good group structure that is good to solve different problems we are facing. So in families, sometimes when we discuss budget decisions, then should I be there?
No, you turn on the video.
Aha.
Okay, no, wait, wait, here.
Because some okay, also.
Yeah, some participants online, they want to see you. So
Okay. Yeah.
Okay. In families, sometimes we discuss budget decisions as in smaller groups, but then next vacation maybe in a larger family, and so in organizations we change. We are going to have many meetings during the day-to-day, and in broader scales we organize in social movements, in political systems, and so on. And so this is all really good. Other animals also reorganize and restructure, but we are really flexible in doing that. And as we're structuring different groups, we also change the way we make decisions in these groups, collect information from each other, and so on. And this is kind of fascinating to us because it's almost like vision. Before you start implementing it in a computer program, you don't understand how complicated it is, how advanced this is. This our sociality and our understanding that certain problems require certain social structures, and this almost automatic change of the way we communicate with each other in a group is, I think, equally fascinating, and we want to understand this more rigorously than just, me talking blah blah. So in particular, it is interesting when it fails. That's when we notice it. So this is the family, the TV office that sometimes fail. We all have it in our lives, but also on a broader society, we have certain failures, and then that is when we notice, and that is when we start asking, why is it so difficult? We all know that something should change, that we should do something. Maybe each of us has some solution, but just collectively cannot do it. And so our approach to studying this is to understand it as a complex system of cognition, social structures, and problems we are facing, where cognitions are, of course, we have many cognitive processes are important, but here we are focusing on those that are important for social interactions, and I'll talk about them a little bit more. Energy cognitions, and these cognitions are embedded in social structures, and they also interact with the problems we are facing. And all of this is changing over time. So as new problems emerge, so our cognitions and our social structures also change. So if at the beginning, maybe the economic development is important, then we are using, and we all have this belief that maybe we are using something like democracy to solve these problems, and we are organizing relatively interconnected networks, flat networks. But if now the biggest problem become outgroup conflict, then we are really quick in reorganizing ourselves in more hierarchical structures, following the leader and so on. Okay, this is how do we study all this? How do we make, especially how do we make quantitative models of this? So if you can say something more rigorously, that's a challenge because many of these different components of collective adaptation can be studied in different disciplines, cognitions in psychology, cognitive science, social structures in sociology, political science, organizational science, problems in their own disciplines. So COVID was, at least at the beginning, mostly tackled by epidemiologists. Climate scientists are doing climate science. This is all without much input of these other sciences, at least most of the time. And then the models are done by you wonderful people who are physicists and mathematicians, computer sciences, but not everyone has the benefit of being in such an interdisciplinary setting, and many of this important knowledge about human cognition and sociality is not adequately represented in some of these models. So how to put it all together? And then even just in social sciences, it is not like we now invented collective adaptation, nobody studied it before. It has been studied under many different guises for a long time. And so even within social science, you have silos between these actually very related approaches, but they rarely kind of cite each other or learn from each other. For example, we have this whole, of course, psychology studies social learning since forever. There is enormous amount of theory and research on that. But research on like wisdom of crowds, so what makes some groups smarter than others, or on collective intelligence, which is an organizational science, or collective problem solving, exploration, exploitation, is really actually interacting with social learning or with each other much. And you have a whole separate research on group decision making, what makes these groups make good decisions and how they exchange information in group interactions. And then yesterday we were talking, the whole program on belief dynamics, tons of models, which is, belief dynamics is just, in essence, it's learning from each other and updating our beliefs based on information from the social environments. But it's mostly not drawing on these other aspects. Then we mentioned briefly yesterday, cultural evolution, game theory, the whole philosophy of group minds. What does it mean to have a group or collective minds and collective consciousness and so on? All of that is relatively disconnected. So we have this ambitious program to at least kind of have in mind all of these when trying to understand collective adaptation. And so how to go about this? Yes, how to go about this? So we would want to create models of collective adaptation. We wouldn't want to stay with just qualitative descriptions of different situations. We would like to have quantitative models that can make some predictions that we can then test empirically. But how do we make a model of this complex system? These models should obviously be somehow simple so that we understand them, but at the same time grounded in what we know about cognition and sociality. They should represent this dynamic interplay. So there should be some dynamic updating, and they should produce these quantitative predictions. And this could be difficult, as you know, from the seminal paper of Phil Anderson, that more is different. When we go to higher level of complexity, sometimes we need entirely new laws, concepts, generalizations. So psychology is not applied biology, or biology is not applied chemistry. So there is more, we need to develop maybe new conceptualizations. But do we? So what we want to look at now is what models do we already have of these building blocks, and then start thinking, how can we integrate them all together? So when it comes to cognitions, as I mentioned, there are three types of cognitions that are particularly relevant in this collective adaptation context. One are social interaction strategies, beliefs about problems that we need to solve, and then finally the social emotions. Now, when it comes to strategies for social interactions, we are lucky that many computational models have been developed, starting from the mere social sensing. So this is the way we actually perceive who is around us, who is in this room, who knows what, who is connected to whom, and what can I conclude about the broader Dutch population, academic population, various others, based on what I see here. And there are some of us that we worked on it and others on how people make this inference. It's pretty simple. It can be specified in an algorithm, in an equation. Then there is tons of strategies for integration of social information. I'll talk about it more on the next slide. And then other strategies for coordination, so norms, social conventions. These also can be thought of as computational models that are dynamically evolving. And then cooperation, of course, there is a lot of these little algorithms for cooperation that can also be modeled. Network building and vision based on preferential attachment, homophily, other things. So all of these are kind of little parts of the, if you wish, a bigger computational model that we could build. Especially when it comes to this integration of social information, which I will mention several times in the talk today, so I'm focusing on that. This has been studied under many different labels. Social learning strategies, belief updating strategies, group decision rules, voting procedures, aggregation procedures. And here are some examples. Follow the majority, follow average, follow best. Those are all, they can all be used to understand how do I learn from all of you, how do I integrate this information, how do we make group decisions, how do we vote. All of these are basically the same strategies. And there, of course, they have different outcomes. So if this is a structure of our network, then if you follow majority, we will choose 1. If you follow average, it will be something like 2. If you follow best or biggest, it will be 3, and so on. And so when you look at them, and we review this literature on these strategies, you can think of kind of 3 somewhat different classes of these strategies. One big class are different frequency-dependent strategies. So majority rule is most popular, but also, of course, there are more. If there are more options, there's plurality. Sometimes we want unanimity. Sometimes we want to be different in some ways, so we use minority rules. The complex contagion that's now popular in sociology, that's nothing else but one more frequency-dependent strategy. And this can be studied and discovered and rediscovered over the centuries in different disciplines. And so when I mean studied and rediscovered, it means implementing some kind of computational model or analytical model and studied what are the consequences for social dynamics or group decision making and so on. Similar for averaging strategies. Now, this has been also studied and rediscovered under different names from the of course, Galton's Ox, the Groot's models, advice-taking literature in psychology, which is all about averaging my opinion and opinion of others. Statistical physics, various using various ferromagnetic models, then cultural evolution models, network science like contagion. All of this is some kind of averaging at one time point or on average over time. And then the third class is actually some extreme version of averaging with weights, where just a particular model is followed. So one of you is chosen based on a certain characteristic, either because of expertise or most similar to me, or I like them most, and so on. And then I follow that one or a few people. And this has been studied a lot in cultural evolution and social psychology, constitutional law. So, like when you think of almost any belief updating strategy, social learning strategy, voting strategy, you can put them in these three classes, and they're ready-made ways to model this. Okay, then beliefs about problems that collective should solve. Of course, if we as a group have different beliefs about what we should be solving, should we deflect another group that's attacking us or solve climate change, there will be some problems for our collective adaptation. And so it's important to understand how we form beliefs and how collectives agree on what is important. And yesterday we had a whole workshop about this, and and we discussed how there are many computational models of belief dynamics that have been designed in following different traditions and different analogies, from epidemiology and ferromagnetics to Bayesian evolutionary models. And currently, as we saw, so yesterday, inspired by Hans' work and Jonas' work, we are working on networks of beliefs approach to the belief dynamics. And then finally, there are social emotions. I'm Croatian, and I don't know how many of you have these strong emotions, but when I watch Croatian football, I transform into the flaming nationalist, and I'm super happy when we score, and I'm very sad when we lose. And this is very important, I think. It's not studied enough, because emotions are sometimes almost shortcuts that can move our whole collective in a particular direction when it's needed. For example, we know it best when there is a out-group threat. When wars start, there is a quick mobilization of people following like national pride, the fear of out-group, and so on. And so this, I think, is the next challenge. It will be really interesting to develop more computation also social emotions. There are some, but it's interesting to think, is that yet another belief in a belief network, or is it some kind of field, or that colors us, or what is this? Okay. So that was about cognitions. And now about social structures, again, a rich area full of different models of social networks, of their size, structure, connectedness, and how this affects our perceptions. A little bit less studied about perceived versus objective social networks, because really there is no objective social network. We all imagine there is something in our head that changes flexibly of what the relevant social network is, depending on the task we are solving. Then there is different models of how of effects of communication technologies, and then the whole literature on how social norms develop, how institutions evolve, how cultures evolve. Computational models are starting to develop also there in the development of culture. And yeah, so this is also promising. And finally, how do we model problems? Well, many people have thought about it as well. We can define, depending on the task, we can describe the problem structure in different ways. For example, most basic is this a categorical or a continuous judgment? Is this a simple or complex problem? Is this a one-shot or repeated problem? Is this what layers of uncertainty we have here? Is it mere probabilities or something unknowns, and so on? What is the rate and type of change? Or what is the structure of incentives? Are they more cooperative or more individualistic? All of these can be also implemented and they're in the computational model. So how can we put it all together? So again, there are some useful paradigms for modeling collective adaptation. I will be showing briefly an example from reinforcement learning, but these kinds of paradigms could actually be useful to integrate these building blocks and to understand how collectives, for example, learn about what are the best combinations of network structures and decision-making strategies. The models of fast and frugal heuristics are promising because those are little computational models of strategies that we can put in at different parts of this dynamic model. Game theoretical approaches, especially evolutionary game theory, are promising, but also models from other sciences. So I will be showing some adaptive landscapes, models of cultural evolution, of adaptive dynamics. Those are all useful models. There are statistical physics models, ecological models also. We can think of human collectives as an ecological system where there are many interactions that are somehow develop over time. But what I think is most promising approach is to have this kind of multi-level computational models where you have, it doesn't have to be one big model for all of these levels. It can be some level at modeling on the level of cognition, which are through parameter interactions related to the models of social structures that are related to problems and so on. You can imagine all kinds of errors. And there is really promising research from the Max Planck Institute and Princeton people in close computational biology recently that are really inspiring to me. But I think this is probably the way to go, to kind of stack them. Find the most appropriate models of cognition, structures, problems, and interrelate them with each other. Okay, so let me give you an example. This is now a very, very simple and old example that we did in 2016, but it just shows why is it important to study all of these building blocks together? Why can't we just focus on cognition or just on networks? So the motivation for this research was that at that time there was, and maybe still is in a way, people were asking what is the best network structure to foster collective intelligence? How should we organize our teams? Should we have kind of poorly connected networks, slow, where we only meet occasionally, where we occasionally exchange information, or should we discuss all the time? Should we be tightly connected? And there is some contradictory finding in the literature. So this very prominent paper found that actually it is the less connected networks usually model as this ring lattice is better over time than the fully connected network. Usually it's presented like this. This is the group score over time. This is the group score. And then you can see that those who are in the less connected network, they are at the beginning slower, but later on they are able to find a better solution. Whereas there was also other research at that time that found the opposite thing. In a similar task, they found in an experiment that actually fully connected networks are better than slow. And so this has sparked a lot of thinking and what is it? Why is it? And so Daniel and I thought, well, it could be that it's about interaction of the building blocks. Usually so far the research was modeling these network structures, but disregarding the cognitions. And okay, so we said, let's do a computational models that have all of this. So we have this fast network and slow network. We go a little bit further and imagine that you can either take a small sample or a large sample from each of these networks. Then you have these different social interaction cognitions, in particular social learning strategies. So how do these people integrate information from their social network? Do they follow the best member, which is a more faster strategy? Because at every given point, there is usually somebody they're solving a complex problem. So there are many possible solutions, thousands of possible solutions. So if you're sampling a group from your overall network, at any given point, there is a high chance that there will be somebody who is a little bit better. And so it is possible to copy almost every time. Whereas if you decide to follow the majority, necessarily you will have to wait a little bit until one of the solutions becomes at least a little bit more prevalent than others. So this is a slower strategy. And when you're not copying, you can explore on your own. So that's true. And then the problems. How do we model problems? Following also some of the previous literature, we were modeling problems using NK environments. How many people know about NK environments? Okay, so it's a really nice computational way of designing more or less complex or simple problems. It has been described by Stu Kaufman at Santa Fe Institute in the 80s and Simon Levin, who otherwise also shows up on these slides, the dynamic dual. Anyhow, so N refers to the number of bits that are either 0 or 1, here represented as geometric objects, like in some of our experiments. And K is the number of bits that the payoff of each bit depends on. So the payoff of this triangle might be, if k is 0, might depend just on this triangle, but if k is larger up to n minus 1, it can depend on k other items. And so depending on how many other items it will depend, you will get this problem landscape that has either one globally optimal solution, or you have this more rugged landscapes where you have this lot of this local optimum. So it's very nice. You can easily program such problems and then use them in both simulations and experiments. An example of a simple and global like problem space with globally optimal solution is, for example, designing a drinking vessel. If you want to design a drinking vessel, they can be in different shapes, they can be in different colors, they have various decorations, but basically it's a cylinder that's closed on one end and open on the other end. So there is a global optimum for a drinking vessel. But when you think of, for example, driving vehicles for transportation, there are many different moving parts, and depending how you put them together, you can get a car, or you can get a bicycle, you can get a train, and all of these different things will interact with each other, and you can get stuck to different local optima, like in a car situation or in a bike situation and so on. And it can be difficult to move from one optimum to the other because of these valleys or the temporarily lower, like less good solutions that you need to cross before you go to the better solution. So that's okay. So now we did in this initial study, we did a computational model where we had these networks. We had agents that were either following the best member or majority or these other control strategies. We had two types of problems, simple and complex. And so what did we see? So for the simple task, it is always good to have fast learning strategies. Now we just focus on the fully connected network. And here we have the red ones are the best member, the fastest strategy. The blue ones are the majority strategy, which just takes a bit longer. And then we have individual learning and random copying at random. And we see that those who are just greedily copying, they are fastest to climb this single pit landscape. And this is because they're able to reduce the diversity of solutions really fast to the one that's best. Okay, but now.
Oh, what do you mean by diversity of solution? Is the entropy or what is the diversity?
This is just a number of unique solutions in a group. There are 100 agents. At the beginning, they're all initialized with a different solution because this, if n is 10, you have if n is 10, you have 1024 2 to the 10. You have 1024 solutions. Each agent has a different solution. And now they are searching the space and they're trying to find which one is the best. And so they quickly copy from each other and they reduce to just one solution, which is the best one. Does that make sense? It's just number.
Yeah, but my solution is like the state of the agent, right?
Yes.
The choices.
Yes,
Yeah,
yes,
okay.
the current solution of the
Yeah.
agent. Yeah.
Two questions. One, is it the right analogy to think about this as like a evolutionary algorithm on a network? And then you've got different crossover operators.
Yes, you know, think of that. Yes.
And then the other question, maybe you'll get to it, but here there's the idea of optimal. But if you think about sufficing, another criteria for solving is time.
Yes.
How quickly the group reaches
Absolutely.
consensus.
Yeah.
So these may have different kind of.
True.
Okay.
Yes.
Okay.
Correct. Yes.
So why does random copying converge at all? How is the selection done?
So it's like this. So you look around and you copy anyone, but it only sticks. You only copy it if it's better than yours. Right? So it's okay. This is all in the simple. Now, what is interesting is, and to your point, is when you have a complex landscape. Now it is the majority of just a small sample. So I can look at 100 other people, but I just select 3, and I take the majority of them, and otherwise I explore. And so that strategy, it takes a while. So if the time, if the time is short, then it's better actually to just greedily copy or get faster to something, to a reasonably good solution. But if a group has time, then they should spend a little bit more time exploring and exchanging information, and then they will reach the best possible outcome. Then when it comes, for example, individual learning, it's good, it explores, but the problem is somebody finds the best solution, but nobody copies them, and so the overall average performance of the whole group is better. And so why is this good? Again, it's because it kind of manages this diversity. It maintains the diversity of solutions long enough until the best possible they could find is found, and then they converge on this one, as opposed to individual learning that never converges, and the best member that converges too fast along this local optimum.
Sorry, I'm
Yeah.
not sure, so are agents homogeneous strategies?
Yes, yes.
Okay, and they're constant over time.
Constant over time, which is the main problem, and we'll get to it next. Mhm. So this is like static, super simple example just to show how these interactions work. Okay, but to the confusion in the literature about what is better, a fast network or a slow network, we find that there is this interaction, and it really depends on what learning strategy people are using. If they're using a best member rule, which is a fast rule, then actually the slower network is better than the faster network. If they're using a slow rule like majority rule or plurality rule in this case, then the fast network is better than the slow network. And so this explains this contradiction in the literature, because once you go into these studies and you see those that find that slower network is better, they actually use the best member strategy. And those that found that fast network is better, they actually use the frequency-based strategy, something similar to the plurality rule. And so there you go, voila, solved. Yeah.
So these slow networks, is it specifically of this ring type, or is
Doesn't
it
have to be.
sample over sparse network?
Yeah, we tried many different configurations. So basically, we can look at average path length is the best approximator of this
Right.
flow.
But does it also depend on the degree distribution at the end of the day?
Yeah, I mean, to the extent that average path length would depend. On the degree distribution.
Yeah, yeah.
Here we had the same degree for everyone. And we did not actually look at the different degree distributions. But I guess it would, it depends how quickly information spreads. If the network is such that information quickly spread, then we would have a kind of fast. So it's all about average path length.
Okay.
Okay, but as you said, this is all static and not changing over time. So now we're going in that direction. So in our current group, we are kind of trying to understand how these buildings block evolve over time. You can think of collectives actually themselves traveling some meta level landscapes, if you wish. So if you define these landscapes by different network structures that collectives can have and different cognitive strategies, then you can think of collectives as trying to find the best combination of network structures and cognitive strategies depending on the task that's currently important. So let's say that at time one we are under attack, there is another group, and maybe we find that for that a certain network structure and certain strategy are best. Maybe being hierarchically organized, following a leader. Okay. In time two, we defeated the group. Now we need to develop economy. We need to innovate. We need to solve various kind of technological, and scientific problems. There, maybe we need a different network structure, different cognitive strategies, which are maybe less hierarchical, more horizontal, with more direct exchange of information. But then let's say that in time three, there is COVID happens, and now we need to quickly, we need to restructure. Now we need to start again following some kind of expert. We need to completely dismantle our networks. And so you can see from this that it becomes interesting because it will depend on where a society was to understand how quickly they can go to the optimal solutions. You know well that some countries were better or worse in reorganizing themselves in times of pandemics and being able to listen to their experts, being able to restructure their networks. And that, according to this view, will then depend on what kinds of problems and what kind of structures they had before this happened. And so now we can go beyond this whole, I don't like this term collective intelligence whatsoever, because intelligence also in psychology is abused and kind of outdated concept, but more in a sense of this collective adaptation, to understand that we are all trying our best, but are coming from we are in different parts of this landscape, and it will take us some time to cross different valleys and to find a good solution depending on where we are. So what might look like collective stupidity I think it's a useless term. It really doesn't say as much except to derogate another group. But we can think of path dependence, where past adaptations, the way we were solving problems in the past, are now sticking with us and affecting our current problem solving. We can think of also collective myopia, in the sense that if you are living in a particular culture which always did things a particular way, it might be difficult to even imagine that things can be different. And so it can be difficult to see that there is a better spot and how to get there. Okay, so now in our group, we are starting again, very simple. So we now have changing problems. We imagine that over time, a collective needs to solve first a simple problem, and then a more complex problem becomes more and more rewarding over time. So now the collective needs to learn best strategies, and let's say that collective can have two social integration strategies following best and following majority. We have two network structures, full and sparsely connected, and now it needs to learn what of these they can use. And the question is like, can we even learn this? Is this possible? Like, how does this even work? And so this is where we are. So we are doing a simple reinforcement learning model where the value of these different combinations is updated on every time step based on the payoffs we are experiencing with a certain learning rate. And so we know that from the previous study that in the simple environment, the collective should ideally learn to follow the best member and be fully connected, whereas in the more complex environment, the collective should learn that now they should follow best but disconnect or follow majority in a fully connected network. So that would be the optimal or the best solutions. And so these are some first results. And what we see is, so there are many lines, but let me just, so this line here, so here, this until round 40, they're in a simple environment, and then it changes to the complex environment. And they do find in the simple environment, this is a preferred combination of these strategies, is that follow best in a fully connected is best. So they prefer that. And then when the environment changes, it takes a while. They do find that following majority and fully connected is better. But then you have this whole other, these are different versions of sparsely connected networks and these frequency-based and so follow best and follow majority with different sample sizes. This is all kind of bungled. There are other solutions here, but the problem is, I think what really is happening is there is this path dependence. People are used now in following, in having or people are agents in reinforcement learning model. They have a lot of experience with fully connected network, not so much with sparse. And so when the environment changes, it will take a while here to discover the sparse network. And we can also think of collective myopia and so on. So you can see this is a difficult problem, and that's something that we will be investigating in the next months and so on to see how is this possible? What could be done to help collectives to figure this out, to start exploring options that they did not explore before, so that they see that they are potentially beneficial. I find it super interesting. And of course, we'll also do group experiments to test some of these predictions. Yeah.
So it seems like actually near the end it's changing its mind again, that it's switching back to follow best.
Right. I mean, you mean, yeah.
Is the relative weight also changing then again? Or is this?
You mean that we just record this value of different options, and then this is the overall preference for it. But yeah, there's obviously a lot of noise and a lot of things going on here, okay. Which is also related to these ones. So maybe they're starting to discover something here that this green is also a majority, but from a larger sample. But so maybe that I'm not sure. Yeah. Yes.
So I'm not sure if this got, how do you model this tension between individual and collective outcomes? Is it altruism? So do agents care also about other people's outcomes or only their own?
Here we are just taking, so the payoff is just my own payoff. So it's just individual payoff. We didn't yet go.
Can you observe how other people fare? Like, do you know how they're doing it?
No, it's just my outcomes in this very simple model. But there is obvious extensions then to see, so that part of my payoff also depends on the collective outcome, and that there could be different tensions here. Yes, so that's a great question. Yes.
So this is very similar to the work that is done on yeast and bacteria on changing environments. I don't know if you're familiar. So for instance, you can put these populations of bacteria in yeast and you change the sugar source, or you change the temperature, and then you study how these collectives of bacteria adapt to these very fast changing environments and the strategies that they choose. And often what happens is that some of them choose to be switching on and off, like different strategies, so that they edge their bets, and some of them become focused in one and on the others, and it seems like very similar. And even the way that they're modeling, I don't know if it's because there's a lot of then stable points that are identified. These collectives, of course, bacteria are different because they are their own, right? But it seems extremely similar in terms of edging different strategies. And
no, you're right. You're right. We're actually inspired also by that literature to understand what might happen if the change is faster, and we know some of that, but kind of neglected in the last few months. But I agree, we should go back to it and see whether any of these applies to this situation, because you're right. Yeah, a lot has been done in how the strategies changed and how this depends on the environment, on the speed of environmental change and so on. Yes, good point.
Yeah. So can you explain a bit this small inset, like reward here is reward by per agent or reward over the entire set of agent?
It's reward over the
Per agent. And how?
This
One. This is high.
Yeah. So the average reward of all agents.
And this increase over time.
And this increase over time, so that if you are solving well the complex problem, the reward is better than if you are solving well the simple problem in this case. Okay, so this is that kind of thing. So that's where this is kind of direction we are going. Another direction here that we want to go here is to see, okay, even if different people experience different outcomes, at the end, maybe they need to choose. So here we force them to basically vote. So everybody has their own value, and then we force them to choose to be homogeneous, to choose one of the combinations of strategies and networks. And currently they are doing this by democratic vote. But you can think of people allowing them to choose a leader, or to have different threshold for this democratic vote. So now we can start thinking, when do people decide to choose a leader? Do they stick with that leader too long? And so on. Anyhow, it's a rich paradigm for this studying this collective adaptation. Okay. And now for some empirical studies. All of this modeling is nice, but we need to actually test it somehow. So we plan to do all of these group experiments. You saw these pictures. So people are asked to choose different combinations of these bits. So you can either choose or not choose each of these items. The payoff will follow either a simple landscape or a complex landscape. You can also see other agents and so on. Surveys, we also do studies of real-world collectives, because all of this is very abstract and very idealized. So we also want to see in the real world, are we missing something? If we are just interviewing people, how they actually make decisions, how they organize themselves from scratch. And then we're also doing various computationally aided analysis, NLP, and agent-based models. Okay, so here's an example of experiment, also work in progress on outgroup threat. And so if you look at our whole system, here we are focusing on the interplay of problems and cognitions. And this is something that was interesting coming from Balkans and seeing like how the whole society changed when I was about 16 in response to outgroup threat. And now when you think of Russia, Ukraine, or Israel, Palestine, there are strong societal responses to outgroup threat, where somehow it seems that from one day to another, we need to choose a side, we need to homogenize. There is a strong pressure to not have different opinions. It's pretty amazing actually how fast it happens. And to this day, this fascinates me. And so we're thinking a lot about how does this outgroup threat affects collective adaptation. And this has been studied in many different studies. It has been found, especially in the military psychology and so on, that it's beneficial to have a homogeneous and cohesive groups. That's why military has uniforms and all these protocols and rules. And then there was also research on whether groups under threat perform better or worse on a range of tasks, from brainstorming to doing something, solving some problem together. and the findings are mixed. And then we thought, well, it could be that under threat, groups tend to homogenize, which lowers their diversity, and then it will be beneficial when tasks are simple, but lower diversity will be harmful when tasks are complex. So maybe if we study tasks and cognitions together, we will find a little bit more understanding of this trade-off. And so our hypothesis that in times of threat, groups will have a lower diversity of solutions. Because they will copy each other more than explore individual at times of threat, and that lower diversity will hurt their performance on complex tasks. And to do that, we did extremely subtle manipulation, like super abstract, just to see, okay, can we get anything? So this is our group experiment. There are 74 groups, on average 7 participants. They look like this from 5 to 9. This is the task. They need to find the best combination of these. They have, I think, 20, 30 rounds to do it. And they see their payoff here. And in the threat manipulation, we just tell them, there is another group. It was a deception. But we said there is another group, and if this group ends up being better than you will get a little bit, I think, like 30% less payoff. If this group is worse than you'll get 30% more payoff than what you earn by exploring on your own. And in one group would get that this other group was always lower than them, and the other group it was always higher than them, just a little bit. That's all. That's our threat. And this is just manipulation check, and we see that when the threat from other group was high, they actually evaluated after the experiment that they felt that the threat was higher and that their decisions were more affected by the other group. So that alone, to me, although we didn't confirm all the hypotheses, that to me it's already fascinating. It's this crappy little manipulation, and people react like that. People, oh yeah, it's threatening. I'm affected by the other group. Isn't that amazing? Anyway. And it's all for like 50 cents more or less. Okay, so what we find now we can look at the strategies that they use to solve these problems. This is again the same thing over rounds. And then this is the percentage of participants who use different strategies. This is percentage that keeps the previous solutions. So they just repeat over and over again what they did. This is the percentage that explores individually or that copy another participant. And these first two are unsurprising. It is often so in these experiments that people start by exploring more, and then they find something satisfactory, and then they just keep on repeating that also. But interesting that also copy pretty stable over time. And most interesting that this is more likely to do when in this condition of high threat. And they consistently copy more. And now the question is, who do they copy? You could imagine that in times of threat, you want to copy somebody who is similar to you, maybe give you some comfort, or you think that this person is somehow in a similar situation with similar skills, so whatever they do might be a good solution. Or you might copy somebody who is kind of representative of the group, somebody behind which the group could homogenous together, somebody who could be a representative, a leader of us. Maybe Han represents all of us, you have all the knowledge of the group, and somehow you're like, yeah, I'm going to copy Han. He's going to represent our group. And it's often found that leaders are actually they're not the most exceptional individuals. They are those who actually channel most of the opinions of the group. And that's what we find. This is distance from such a person, and this distance is lower for people under high threat. So it's not that they copy similar to self. They copy someone who is representative of the group.
That just means their strategy is closer to the average of the group.
Yes. Or when they copy, they will copy whoever is currently most representative of the group.
Okay, so that one person who's the average of everyone else. Okay.
Yeah.
So they see a convergence and move to it.
Yeah. And now the puzzling thing, it didn't affect their performance. And so we were hoping that in the simple task, because the diversity is lower, that we'll get better performance under high threat, and maybe a little bit, but it's so much noise that we don't get this. We would want this red line to be much higher here and much lower here. This didn't happen. So now what we need to do is to do more work to understand what's actually going on. And somebody is watching Windows. We need to watch this and do some more analysis, because it's interesting actually how the group adapts somehow, but it did not lose on performance. So that's that. And then my last empirical study I want to show is something now again completely different, which is also in a way, but this is now very real world. This is collective adaptation to hate. This is something we're working on for the last few years in this excellent group of wizards, various computational wizards. And so first, so which part of this of our little system is this? First, we're focusing on how in these different situations, so how the hate is addressed by different social structures. So our problem here is hate, and now we are seeing how the collective online organizes to conquer this hate. And so hate is defined as insults, discrimination, or intimidation of individuals or groups, online in this case, on the grounds of their supposed race, ethnic origin, gender, knowledge. And there are consequences of online hate speech because people leave toxic discussions and they don't participate. And it's very careful. I love this set of studies by Carsten Miller and colleagues. Very careful kind of economic analysis that with instruments and everything showing that hate speech online actually has consequences for offline violence. So it is a problem. And so different strategies have been proposed to counter it. For example, let's censor people. But it has people protest, censor. There are all kinds of legal consequences. Moderation is also difficult. Who's going to do it? There is just too much of that. Criminal prosecution takes forever. Authentication, so to force people to identify themselves, that could also squash legitimately endangered voices. And so this is one promising alternative is counter speech, where citizens themselves, when they see a hate speech, they say something. You see something, you say something. So it's a direct response in order to stop and prevent the spread of hate, help the victims, and if possible, change perpetrators' attitudes. And maybe even if you don't change perpetrators' attitudes, you signal that this is not okay, or that there is another opinion. And this has been studied a lot, but mostly in just qualitative analysis. One point of this that we maybe all experienced if you ever found yourself motivated to react to hate online, that you quickly get attacked, it's painful, and you just want to run away. So it's very difficult to do alone. But there are organizations out there, like Ich bin hier, I'm here, it's an international organization where people organize, I'm not sure, on Slack or Discord, they identify where's hate speech being done, and they come as a group. Now, when you do it as a group, that can be easier. It can also be easier for haters, because it's difficult to be the single voice, but if you come as a group, you might be more effective in promoting hate. And this has been discovered by Reconquista Germanica. So Reconquista Germanica was an online kind of hate group, or a very extreme group that has actually unofficially or officially being supported by this AfD, the main very extreme German party, and that had this organized Twitter group that had its own organizational structure, which was actually very hierarchical, and that was organized on Discord and was mostly going to big news sites like Tagesschau and so on. And then when there was some news that I didn't like about immigrants, we are focusing on the time of the height of immigration crisis starting in 2015. There was a lot of discussion, there was a lot of hate, there was a lot of reactions to that. And so they would come to these big news sites and they would hate basically together, organized. And they were quite successful in that until this Jan Bommerman is a TV personality, like a comedian. He said at some point in one show, well, let's organize ourselves as citizens and let's go in groups and counter this. And he was calling that Reconquista Internet. And so you have some examples of their typical tweet. This was all happening on Twitter at that time. And so we had one in our group was actually a member of this Reconquista Internet, and he had some insider information that helps us identify exactly what tweets are Reconquista Germanica or Internet. But also it was not difficult because people were self-labeling. They would have on their Twitter profile, I'm Reconquista Germanica or Reconquista Internet. So we basically have, the problem in machine learning detection of different strategies or points of view is that you need to have a self-labeled sample. So first you need to label thousands of exemplars to classify. But here we have this self-classify because people were labeling themselves as Reconquista Germanica or Internet. Anyhow, so we analyze these political conversations. Typically, a tweet starts a Tagesschau or somewhere on one of the 22 news outlets, and then people come and comment on it, and some of this is hate, and then maybe counter comes, and then we study this with these response chains. This is how we have all of these reply trees. So each of them is a different discussion. Those are actual trees. So it starts from somewhere, and then people comment, and so this is what we analyze. And so after a lot of massage and classifying, we come to this time series. This is now proportional hate and counter speech over time from January 2015. This is the year when the migrant crisis started, and to end of 2018. This is where the Reconquista Internet, the counter speech group, dissolved, because if any leftist group, they existed for a few months and then they dissolved because some were more interested in LGBTQ and some were in climate and so on. Anyhow, so we have around 30% of tweets labeled as hate. They peak around terrorist attacks and so on, as you could imagine. And then we have some counter speech, which is not so prevalent, and it increases a little bit. This is where organized hate shows up, and this is where organized Reconquista Internet shows up after Jan Böhmermann. And now we can see, we can do this Granger causality analysis with all the caution that we can have, but we can see some interesting patterns, and there is much more analysis here you can see in the paper. But basically, before organization, hate was negatively related to counter speech. So the more hate, the less counter speech. But then counter speech was also negatively related to hate. So if somebody counter speaks, hate decreases. But hate was also promoting itself. Now, when the hate starts, organized hate, so they come in groups now, they are become much more powerful. They're suppressing counter speech, but the lone voice of counter speaker is now provoking even more hate. They're particularly targeting this, and the hate is now promoting hate. And the counter speakers are just like the more those individuals that show up, they quickly give up. But then after the organized Reconquista Internet shows up, then we have now counter speech negatively affect hates and promotes more counter speech. Now, all this is just be taken with a grain of salt, because of course this is online developments. But here, for example, there are huge offline rallies against Nazism and pro AfD. So there was a lot of other things going on. So it's really hard to say in these real world environments what's causing what. But here are some patterns that suggest that organized counter speech might have helped. But then we go further, and we can now ask, okay, what exactly should these counter speakers do? We can think of different argumentation strategies that people might be using. For example, they can just give an opinion, honest opinion, without insults, no argumentation, nothing. Just say, yeah, I don't like this, or I like this, I agree, or I disagree. And then, or you can give a more constructive comment. This is what is usually assumed to be a really good discussion. When you provide information, you quote relevant facts, and you point out consequences, contradictions, and this is a constructive thing. You can be sarcastic, you can give insults. And then all of this can be additionally colored by mentioning group identities, mentioning us, mentioning them, and different emotions, anger, disgust, joy, all this kind of thing. A lot of analysis later, what we find out is that this simple opinion, maybe with a touch of humor or sarcasm, is actually the most effective strategy. Constructive comments are not effective and sometimes would even backfire because maybe people thought that they were preached to. Any mention of in-group or out-group would usually provoke more hate. Any emotion, even positive emotion, probably typically because it was kind of I'm proud of my own group rather than I'm happy for you others. This was also not effective. So, which is interesting because it gives us all more power. It's just important to show up and say, I disagree. That is having consistent over many different time scales that we analyze from tweet to tweet over discussions over days. It had the most impact. Okay. There is various other research that we are currently doing. This is our new group. There are also some people from Santa Fe Institute. This is our new building. And so, for example, we are doing statistical physics models and also preparing experiments on how polarization might be reduced by anti-conformism. Then we are also doing a lot of work on belief networks and also measuring individual belief networks from open-ended textual data. We are looking at robustness and resilience belief networks. We are looking at generative agent-based models. We are doing mathematical models of collective action and social norms. We are having a big, there's a big computational model of online use communities and collective adaptation there. And we are doing a lot of these qualitative studies of real-world initiatives. So, keep on following us. Maybe some things will come out of this group. We are very happy to collaborate. All opinions welcome, and we hope that you'll come and visit us. That's that. We have this. Sorry. I also want to say the list of our founders is long, but now one just left. We lost them and said, right? Which isn't that amazing? Like this is the pressing problem now. How do we all collectively adapt to this? To these kinds of things? What's going to happen to science in the short run, long run, society? Answer that, right? So, and that's our vision is huge, and of course we are not merely going to do a little pixel of this, but I think, as I mentioned yesterday, I think really we are the position in social science we can actually be better in understanding how this happens, because we have interdisciplinary collaborations like never before. We have computational modeling power that we never had before, and we have more data about human behavior than we ever had before. So maybe if we put it all together in a clever way, we can say something more about why are we here, where are we going, and what can we do to nudge ourselves out. Maybe also the problem of science in the US. And that's it. Thank you very much.
Is there any question?
That was a really nice talk. Thanks a lot. As you were going through beginning, I was thinking a lot back to the old distributed AI kind of work in the 80s, 90s.
Yeah.
And one thing I was thinking in this kind of collective action stuff is they all have an idea of what the optimal is.
Mm-hmm.
But in the real world, there may be disagreements, or going back to the opinion kind of formations. But then later on, as you were talking about this counter speech and collective action and that thing, I was thinking about the Byzantine generals problem of Leslie Lamport from the. So they had a mathematical proof to show that you need. Yes, so you have a maximum of 1/3 defectors basically to reach consensus. So I was wondering, and I was having a quick look, I couldn't find anything. If you do this in social systems, right? These are AI systems. There's no emotions. There's no kind of messaging kind of question about how that's brought across. Whether there'd be a nice experiment to think if you could prove that or show or demonstrate that the limit still exists.
I love this. Yeah, we should talk more.
The type, because then you talk about the type of messaging might kind of reduce this or increase it.
Yeah. That's good.
Yeah. Okay, I can send you some.
Oh, that would be great. Yeah, thanks.
So I was wondering, when I saw also you mentioned Condorcet work, and one of his results also showed that many of these group decisions are based on the idea that each agent has a slightly better probability of being correct by the last. And I was wondering if that's also true here, because each agent seems to be able to verify better or correct some decision.
So we looked at that. We actually have a little paper.
Show it. You have a slide. Show it. Show.
No, we actually have a little paper some years ago, which exactly this that on the Sedgwick theorem is based on. It depends on the fact that on average participant is more than chance correct. And now it becomes interesting when actually most people are wrong, like before the 2000 election, most people thought that Clinton will win and not Trump. And then one could ask, what is then the best group size? Because if people are better than average, then majority of larger group will be better than individual. But if they're worse, then just choose a random dictator. It's better than having a majority. And that's interesting because we were looking at that, okay, let's say that I'm a consulting agency and I know that I'll solve 10 problems. I will have to solve 10 problems over time. but I don't know whether some of them are going to be difficult or easy. Difficult in the sense that most of our will be wrong. And then I need to now design a way in which we make these decisions. Should I make this consulting agency large and have a large group? Should it be small, or should I designate a random person? And so, well, long story short, then you can see that for various combinations of these task difficulties, you get an intermediate. Now you get a non-monotonic benefit of group size, so that groups between, I don't know, 5 and 15 are best in most cases, and in the long run, you're not sure whether sometimes there will be this very difficult task.
Yeah.
So, but yeah, and also others.
Yeah. Okay, so group size then matters if it's not.
Yeah. That's very interesting. Yeah.
Okay.
Maybe have a question? Okay, then so we
Thank you
can
so
meet
much.
us again and then we go to lunch.